vers toi pour te briefer un peu juste avant.
Hello, everybody. I'm Jordi Baylina. I've been in the space for almost 10 years right now. And today I want to present Zisk. Actually, Zisk is a project that was born inside Polygon. And, well, Zisk is a ZK-VM, very much like we just write programs in Rust or circuits in Rust, and then we want to prove it. That's very much what Zisk is about, okay? So it's a program that, as I was mentioning, it started in Polygon about 1 year ago. We mainly took all the knowledge and all the technology that we had in the Polygon ZK-VM, what was very much the Hermes team a long time. We have been improving a lot during these 2 years. And we took all this, we start building this ZK-VM, and actually we start building Zisk, okay? And the thing is that 15 days ago, we just spin off from Polygon, and we are kind of a free project, own project. We are an open source project, kind of a community project, and we want to keep developing this technology. Why we spin off from Polygon? Maybe you can ask, and there is a good motivation for that. In one side, Polygon is focusing more in the aggregation layer and in more higher level protocols, and they want to be free to choose the best ZK technology that's in the market. Okay, and in the other side, we are, we don't want to have a single customer. I think the technology is much better just to be used in a single place. I think that this technology can be used, anybody should be able to use, even if it's a competitor of Polygon or someone else, okay? So we just spin off, we just take the team, and yeah, we are outside, we are getting in a startup mode, we're having a lot of fun, and this is what we are doing. Mainly we just take, well, this is more the details, but mainly we just take all the IP, we just take all the knowledge, and we just continue the project and trying to be reference ZK prover for the space, because we need it a lot, okay? So we can, actually you can follow us here. I will put that same slide at the end of the presentation, okay? But what's the differentiation? Why, what's this good at? Okay. So, well, the first thing is that from the first day, we want to minimize the latency. Okay. Until now, in the ZK-VM, for example, the beginning was just trying to prove. That was a big achievement. But then we tried to minimize the cost of generating the proof. But we realized that we need, in the modern protocols in the future, every time we need more to load the latency. So in Zisk, we took this as a requirement from the first day, and we rebuilt everything in order to be able to prove as fast as possible. And we are trying to push the technology as hard as we can so we can generate proofs in real time, as we are going to show in this presentation, but even farther than that. Okay. Why proving in real time is important? Actually, whatever you are going to do in the space, you are going to need this. You are going to need this if you are a layer 2 and you want to build a roll-up. You are going to need to build some circuit that proves the transition in the layer 2s. If you are trying to communicate between chains, and I'm saying L1 to L1, L1 to L2, L2 to L1, or whatever combination you want to do, you want to prove. The aggregation layer, for example, this is the big motivation why we started the project. You need the chains. In order to communicate to other chains, you need mainly two things. One is to commit to the current state, but the other is to prove that this state is valid. You can do that by following the chain, but if you have thousands of chains, that all the chains follow the other chains, this is not practical. So the idea is that each chain prove that this state is valid, so that the other chains just can take this proof and verify that. Okay? So if you are communicating between chains, this is valid. This is important. But again, and the other part is for layer 1s. And layer 1s, we see, for example, in the Ethereum Bean chain, they call it somehow the ZK consensus, and this is used in many places and can be very useful for scaling L1s. Another thing to mention, for example, is in the light clients. If you want to prove the full chain and verify it in a mobile phone, this is an important technology, and for that you need to prove it in real time. So I'm sure that in few I mean, a few months or years or whatever, we are going to see that all the blocks include some sort of ZK proof in the consensus. So that's why it's important, and that's why this project makes sense, and that's why we want this to push this project and pushing hard in this technology. Properties of this project. Well, as I mentioned, it's designed for fast latency, and that means that it can parallelize a lot with multiple servers, not in a single server, but in a cluster of servers. It's a full stack. I mean, we built everything from scratch. We have all the pieces in host. It's a 128 security. I'm going to highlight that later. We are fully open source. I'm going to highlight that also later. It's a RISC-V. It's a 64 bits. I think it's the only, currently, I don't know if there is other projects, but it's currently the only of this kind of these 64 bits. This is interesting because, for example, if you want to prove programs running in Golang or in C#, then you will need these 64 bits. Also, it's slightly more performance at the 32 bits, especially for memory transfers and other things. And again, it's this technology is, I mean, it's not only for proving a VM. I mean, it's just a full prover. Okay, we will see that in the stack. Okay, but I want to highlight these two things. The first is 128 security. I mean, we are seeing in the space that we are starting seeing 100-bit security. A lot of projects are doing 100-bit security. I mean, this is not a pizza. This is not a pizza option. This is a must. And maybe it's a personal thing here, but I mean, security. What we are selling is security, and we cannot low this. I mean, we could spend in our team. We could spend maybe, I don't know, 2 weeks, 1 month in doing 100-bit security, but we are not going to do it. Security is important. 128 bits is important, and I'm calling from here that all the teams should go. I mean, if we want to compare, we need to compare with the standard 128-bit security. If we decide 100-bit security, then let's low all the security for all the Ethereum. Let's change the signature schemas to 100-bit security, or the hash functions to 100-bit security. But this is an important thing, and this is something that we are committed in our team to keep the security as high, keeping the high standards that we have in the Ethereum community. The second is open source. I mean, I don't want that in order to build a block on Ethereum, you need to pay some kind of royalty to some private company. This is not acceptable. We need to be open source. I mean, all the code that needs to be in the space needs to be open source, needs to be available, and needs to be free to use. That's why also we are committed to this. I put in these two things big because I think these are two commitments that are important that in the space we need to take in account. As I mentioned, ZISC is, I mean, we have the VM is one piece, but actually we have a full proof, a whole full prover, full CPK prover that's built on top of that. Actually, in this prover, we have a build-to language. I mean, this is an extension of the build language that we built in the ZKVM. This is all getting all the improvements and all the knowledge that we get from there, actually, to build the new system, the new modern proving system. We have also the recursor that allows us to join many proofs generated with the proofman. It allows us to join many proofs and I mean to aggregate these different roots. Okay, but this is a full ecosystem thinking on any ZK prover. Okay, not only the ZISC VM, which is actually the one that we are selling and what we are showing today. Okay, but this is a full stack from bottom to the top. The main difference between PIL 2 and PIL 1, or if you wonder the main difference, I mean, the thing is that actually, instead of having a single monolithic proof, what we do is actually we divide the proof in sub-proofs if you want, or sub-pairs, or many pairs that you want. Okay, so and the idea is that in each proof you can decide how many you want. I mean, if you have a proof that has a lot of binary operations, then you can add more. If you have a longer proof, then maybe in the main processor you will have more chunks of the main processor. Okay, so you end up, if you have a lot of ketchup, maybe you have a lot of ketchups. Okay, and you have different pieces, and then the idea is that we aggregate all of them with in a recursive way. Okay, so this is very much the structure on that, and all that is written in PIL 2, and with all the language you can read it very, very well. Okay. Well, this is a PIL 2 language. I mean, all these state machines, they communicate what we call it to the bus. So the idea of this bus is that when one state machine, maybe the one processor, instead of proving everything in one single machine, actually there is one machine, maybe the processor, that's assuming that maybe a multiplication is valid or that a ketchup is valid. Okay? And what's assuming it, this is added to the bus. Okay? And maybe in another coprocessor, in another state machine, what's doing is actually proving this actual multiplication or this ketchup or this operation and actually subtracting from the bus. So the idea is that the bus, whatever you do in the bus, you subtract it in the bus. Okay? Hector and Roger, they did a presentation before that they give all the details how these mechanisms work. Okay? But this idea of the bus, I mean, at the end of the idea is whatever is assumed in one side needs to be proved in the other side. Okay? So that's why everything needs to sum to 0. Okay? But this is very good, for example, for doing some operations, I mean, interesting things like that. For example, you have multiplications, okay? So you have 64 bits multiplications, 32 bits multiplications, and maybe multiplications that are, let's say, common multiplications. Okay, so you can have, with this system, it allows you to, the processor assumes one multiplication, and if it's a 32 bits multiplication, you are using one state machine that actually is the one that's subtracting. If it's a 64 bits multiplication, another one. But if it's maybe a 1 times 1 or something that's a common operation that happens a lot of time, especially with the small numbers, then you can prove it with a much cheaper operation. So the memories, for example, the memory is a 64 bits memory and it's aligned by default, okay? And most of the operations, they are just the memory, just answers. So this is assuming some memory operation, the operation happens. For the non-aligned, actually what we have is a specialized state machine that's doing kind of the conversion. I mean, it's proving, so proving this read, that's not this non-aligned bit, and actually it's creating, it's assuming 2 aligned systems, okay? And this happens not many times in the command, but you can solve it in a very elegant way like that. Okay? The bus is also, for example, for the continuations. I mean, the idea is that how we connect one chunk of the processor with the other. Well, the idea is that at the end of a chunk, we add this state to the bus, and at the beginning of the next processor, we subtract it from the bus. This is what allows us to connect the things. The same thing happens with memory, but instead of being chunks, temporary chunks, we have for memory addresses, okay? But at the end, it's a state. I mean, the memory, we need to sort all the accesses to the memory by address and by count, I mean, by step. And the idea is that, okay, maybe we have one chunk of memory in one chunk of memory, the next chunk of memory. I mean, so next page, different pages on the memory. And the idea is that we just have a kind of a state transition between one page and the next page. But the idea is the same. I mean, it's a spatial continuation, but the idea is exactly the same, and we can use exactly the same bus. Okay. Another interesting thing is another interesting thing. I don't know how much I'm in time, but another interesting thing is what we call the inner continuations. I mean, because we have a lot of them, you see most of the state machines are quite filled. Okay, so we only have, let's say, wasted space in the last chunk. But as an example, for example, in the current block, for example, we have like about 100 chunks of the main processor, and I mean all of them are filled. It's only the last one that maybe it's not fully filled, okay? So our system allows us to build quite a big proofs, especially if you are using clusters on that. So the efficiency of the usage of the cells that we are using in the memory is quite efficient. But even that, for example, if we decide to go with, let's say, with the smaller machines, or we have a bigger proof, then the idea is, okay, maybe we have a lot and we still have this, we may have this wasted thing, okay? But then we can do tricks that are interesting. I mean, the idea is we can have like 3 connected, we call it these outer continuations, but the idea is that all of them are filled, but here it may be something that, okay, something that we haven't proved yet, or maybe we are proving ahead in here. So there are some operations that maybe are from the next one that we are already proving here, or the other way around. But there is still some operations that maybe we are not proving here. They are pending to prove here, and we pass to the next one. So the idea is that at the end, we are filling even all the blocks, even with outer continuations. So this problem of rounding things is not a big problem for us. Of course, at the end, what's pending to prove in the end, the boss needs to be 0. Okay, so this is the simplified version of this. Okay, we're ready. We're integrating with Fproof. I think we are running in the stage. I don't know if today, tomorrow, maybe this week or next week, whenever it is, we are going to be there. I hope that very soon. And this is the slide that I want to mention, because I think this is the new one, and this is the big announcement that we are doing here in ECC. Okay, and this is that actually we are proving blocks in real time. To show this, we are taking a block that's, it's a quite costly block. It's a block that's, let's say, in the 5% top of the blocks. It's really expensive. There is only 5% of the blocks that are more expensive than that, so it's a high-rate block, okay? And here you see the number of GPUs that we are using. If we are using just 4 GPUs, this takes about 90 seconds. But if we are using 64 GPUs, we are already below the 12 seconds, okay? There is still here some things to improve, and I believe that, I'm going maybe to the next stage. Okay, this is the targets that we believe to use, and we believe that if not all, most of the blocks of Ethereum, they should be able to be proved in 12 seconds. Okay, this is the timings that we are getting. You see that the aggregation is really, really fast, and there is a lot of margin to do that. The Windish computation, this is the one that we are working. We already did a lot of improvements the last weeks, but this is still margin to improve there. Here in the GPUs, we have some balancing things that can be improved. But these are the numbers that I think that in the coming weeks we can easily achieve. And again, working with 32 GPUs, this should be more than enough for proving whole blocks. Still a lot of work to do, but a lot of optimizations to do, and a lot of things in the backlog to do, but we are already there. Of course, this needs to be audited, needs to be, in order to be production ready, needs still some work to do, but we are quite excited, and we are in progress to do that. So that's very much my presentation. Again, you can follow us here, and thank you very much for your time. I don't know if I have one question. Have one time for one question, maybe?
Thank you very much for the talk. My question is about how do you guarantee coherencies between these sub-circuits that you are computing in parallel? How do you make sure the input that was passed to each one of those sub-parts matches exactly?
Yeah, the idea is, this is well, let me just go back. But this is so the idea is that the aggregation circuit. So all this is guaranteed. This is when it's aggregated. This is a kind of a tree, okay, a tree of proof, okay. So these input are inside, so are passed to the top circuit and are propagated to all the circuits, okay. So all the inputs are known for all the circuits, okay. So and because we are aggregating them, we are sharing that. We guarantee that all of them, they have exactly the same inputs.
Got it.
Yep. That's it. Okay, pues thank you very much. And any question, I'm outside.